In this lecture, we're going to briefly review a few of the features of the cosmology simulator Cosmo EJS.
Using the Friedmann equation that we derived last time and matching it to what we observe, we've come to the following conclusion about the content of our universe. We found that 3/4 of our universe, 73%, is made of dark energy. We have yet to discover physically what is causing that dark energy, but we do know it is there. We see its effects. Dark energy is the only form of energy that can cause the universe to accelerate. The other quarter of the universe is made up of matter, and we know from measuring the dynamics of galaxies, as we talked about a couple of weeks ago, that most of that matter is actually in the form of dark matter, some form of matter that is definitely out there because we see its gravitational effects, but we can't see what it is. So we're trying to detect it and figure out what that dark matter is made up of. Only 4% of our universe is made up of normal matter that makes up stars, people, planets, everything that we see around us. The Cosmo EJS simulator allows us to see how we've reached this conclusion. This is a rather big, important conclusion, that 96% of the universe is made up of stuff that we can't see and we don't know what it is. So let me introduce you briefly to how it works. So you'll go to the website linked to in the course material, and you'll download a copy of Cosmo EJS and run it. So let's run it and see what happens. Okay, so when you run it, you'll get a screen like this, which introduces it. And what this simulator does is that it takes the Friedmann equation, which is given in the notes that come along with the simulator. So let me zoom in on it. This here is the Friedmann equation that we derived. It looks the same apart from the dark matter part, which has this more complicated function attached to it, which you don't need to worry about too much. But this equation here accounts for all possible behaviors of dark energy, which we don't know, so we have to account for all possibilities. We have the matter term here. Omega m tells us the percentage of the universe that is made up of matter, and omega k tells us whether the universe is flat, open, or closed. What the simulator does is it allows us to select values of the Hubble constant h0 and values of omega m, omega lambda, and omega k, and create models of the universe to compare with observations and see if it works. So let's go ahead and do that. So what you'll do is, the easiest way to operate this is to select the bottom option here. So double click on the green triangle under Fitting Cosmological Data Compilation. And that will open up a window that looks like this, and a set of parameters down here at the bottom. Okay. So what we have selected here, let me just enlarge this. What we have here is a set of observational data sets. This is a set of data on the distance versus the redshift to various type 1a supernovae and gamma ray bursts, which are also powerful explosions that are thought to be related to supernovae. So these are observations. Each data point is an observation with an error bar. The error bar reflects our uncertainty in the distance to the supernova. If we select a particular value for Hubble's constant and the various omega parameters, then a particular set of values will predict that the distance versus redshift should behave in a particular way. So let's go ahead and do that. Let's select a value of Hubble's constant of 100 kilometers per second per megaparsec. And we can then select various values of these parameters. Now remember, we derived in the previous lecture the fact that when you add up the omegas, they have to equal 1. So at the moment, we can't select a value for omega m because it is computed depending on what we choose for omega k and omega lambda. Right. So let's set omega lambda to 0. There's no dark energy in this universe, and let's make the universe flat. So that means the universe is entirely made of matter. Well, to see what this model looks like, we hit calculate, and you see this curve here is being calculated. This is the theoretical prediction. And you'll see that it doesn't match the data very well. The curve falls underneath most of the data points. This number up here, chi-squared, gives you the quality of the fit of the theoretical results to the observations. The higher this number, the worse the fit is. So for example, we can reset this and alter, let's give the universe 20% dark energy and see how that changes things. So we hit calculate now, and we see that the curve has gone up a little bit, and this number has come down a little bit, saying we've got a little better fit, but it's clearly not very good. So we can reset the plot again, and maybe we can decrease the curvature. Let's make this an open universe and see what that gets us. Well, again, we're not that much better off. So you can play about with these numbers and see what it takes for the theoretical prediction to match the observations. How much dark energy do we need? How much curvature do we need? How much matter do we need? Now you can do this with a variety of the other observations. For example, this is the fit to the cosmic microwave background. It's hard to do a nice plot like this. This shows the results using the data that we've selected so far. It actually displays the chi-squared fit for the supernovae and the other results. And this is the combined likelihood taking into account all of the data here. What your task this week is going to be to try and find the values of these parameters that give the smallest total likelihood given all the available observational data. The set of parameters that give the smallest value here are the set of parameters that best describe our universe.